Have you ever stopped to think about how all the electronics in your life actually work together? I mean, really think about it. The chip in your smart fridge, the dozens of sensors in your car, they're all constantly talking to each other. But how? Well, today we're going to pull back the curtain and look at the secret language that makes it all possible.
Seriously, think about it for a second. If every little part needed its own dedicated wire to talk to every other part, our phones and laptops would be this impossible tangled knot of copper. But thankfully, they're not.
The secret is something way more clever, way more efficient. It's a language that saves space, power, and, let's be honest, a whole lot of engineering headaches. And that language is called serial communication.
So what is it? Well, instead of just shouting all the information at once through a whole bunch of wires, serial communication is like lining everything up neatly. Devices send information in an orderly line, one piece at a time, kind of like cars going through a single-lane tunnel. This is the bedrock concept that makes almost all modern electronics work. And today, we're going to break down 3 of the most common dialects of this language: USART, SPI, and I2C.
Okay, first up in our toolkit is USART. You can think of this one as the original, a super straightforward, point-to-point workhorse that's been getting the job done for decades. Right, so that stands for Universal Synchronous Asynchronous Receiver Transmitter. It's a mouthful, I know, but all you really need to remember is that this was one of the first major protocols used for things like old computer terminals and, later, the COM port on your PC. The whole idea is simple. It's for 2 devices that need to have a dedicated one-on-one chat.
And that private phone call analogy? It's perfect. When 2 chips are talking over USRT, it's like they have their own private, direct line. Nobody else can listen in, nobody else can interrupt. This makes the conversation really simple and super reliable. It's perfect for something like, say, a GPS module that just needs to constantly send location data to a main processor.
And here's why it's so solid. See, with separate lines for transmitting, that's TX, and receiving, that's RX, both devices can actually talk at the exact same time. And, crucially, in its most common mode, it's asynchronous. This just means they don't need a shared metronome or clock to keep time. They just agree on the speed beforehand and go for it. And what if you need to send that signal a bit further? Well, you use something called a line driver to boost the voltage. This turns it into the famous RS-232 standard, which can reliably shout that data over about 10 meters, easily cutting through any electrical noise. But what happens when a simple phone call isn't enough? What if you've got one main device that needs to talk to a bunch of other devices, and it all needs to happen really, really fast? Well, for that, you're going to want to call an SPI meeting.
So SPI introduces a whole new kind of structure, the master and slave. You have one device, the master, and it completely runs the show. All the other devices are slaves, and they only speak when they're spoken to. And unlike USART, this one is synchronous, which means the master provides a steady clock signal, like a conductor's baton, that keeps every single device perfectly in time.
Now this is really cool, because here you can actually see it in action. That chip labeled U1, that's our master. And it's connected to 2 slaves, U2 and U3. The master is in total control, deciding which one of the slaves it's talking to at any given moment.
Exactly. Just think of the master as the boss running a meeting. The boss sets the pace for everyone. That's the clock signal. And the boss decides who gets to talk next. Everyone else just listens quietly until it's their turn.
And the slaves, they're the employees in the meeting. They're all connected to the same conversation, so they hear everything that's going on. But they stay completely silent until the boss activates their specific slave select line. It's literally like the boss pointing a finger and saying, "Okay, Dave, it's your turn. What have you got?" This system makes sure nobody ever talks over anyone else. So here's the crucial point. It's all a trade-off. SPI is incredibly fast, way, way faster than USART. You see it all the time in things like high-speed memory chips or SD card readers, where you just have to move a ton of data and fast. But the downside? Wires, lots of wires. You need one for the clock, a couple for data, and then you need a dedicated slave select wire for every single slave device you add. It can get pretty crowded pretty quickly. So what if you need that organized multi-device system like SPI, but you absolutely cannot spare all those extra wires? Maybe you're working on a tiny device? Well, that's where our third and final protocol, I2C, comes into the picture. It is the absolute master of efficiency. It stands for Inter-Integrated Circuit, but pretty much everyone just calls it I2C, and its claim to fame is right there in the name.
It connects circuits together using just two shared wires. That's it. One wire for data and one for the clock. Period. Just look at this simulation. You've got the master microcontroller, a memory chip, and all those monitoring tools. And they're all hooked together by just those two lines, SDA for data and SCL for the clock. It's just so clean and simple. But wait a minute, if there's no slave select wire, how does the master pick who it talks to?
Well, here the analogy shifts from a business meeting to a city bus route. Imagine all the devices are like houses sitting on the same two streets. Instead of running a private driveway to each and every house, the bus driver, that's our master device, simply gets on a loudspeaker and shouts out an address, "Hey, I'm talking to house number 7." And only house number 7 opens its door to answer. This is all done in software, with addresses instead of physical wires.
And this is exactly why I2C is so powerful for really complex systems. You save a massive number of physical connections on your circuit board. And because every device gets its own unique software address, you can connect over 1,000 of them to the very same two wires. You find I2C everywhere inside a modern smartphone, for example. Connecting the main processor to the accelerometer, the gyroscope, the light sensor is just incredibly scalable. Okay, so we've met our three main players. We have the private phone call, the fast-paced office meeting, and the super efficient city bus route. So how in the world does an engineer actually choose the right one for the job?
Well, this table really breaks it down perfectly. If you need a simple, dedicated link between just two devices, maybe over a slightly longer distance, USA Art is your phone call. If you need the absolute fastest speed you can get between a master and a handful of slaves, and you don't mind the extra wires, SPI is your office meeting. And if you need to connect a whole bunch of different devices using the absolute minimum number of wires, I2C is your city bus route. It's that simple. And this quote from the source material really sums it all up. Each protocol gives you something, but it asks for something in return. A trade-off between hardware complexity, software complexity, speed, and distance. At the end of the day, there is no single best option. There's only the right tool for the job you're trying to do.
And that really leaves us with a fascinating final thought. These protocols, USART, SPI, I2C, they're the absolute bedrock of communication on a tiny, local scale, inside a single device. But as we start to connect everything to the Internet of Things, these fundamental principles of addressing, timing, and taking turns, they're exactly what allow trillions of these tiny, local conversations to scale up into one massive, global one. The big question is, what will that future ultimately look like?